So we now have our expression for the resistance in a conductor, that the resistance in a conductor is directly proportional to the ratio of that conductor's length over the cross-sectional area through which the charge carriers must move, where the proportionality constant we call resistivity. Resistivity is a measure of how strongly a material opposes the flow of electric current when exposed to an electric field. Resistivity is a property of the material itself. Just like conductivity is a property of the material, resistivity is also a property of the material, since it's just the reciprocal of conductivity. Isotropic materials are materials such that their electrical properties are the same in any direction. For isotropic materials, the ratio of an applied electric field to the current density through the material is defined as the resistivity of that material. So that makes sense, because remember, current density is directly proportional to electric field. But that proportionality constant, called conductivity, can be expressed in terms of resistivity. So we could say that current density is directly proportional to the electric field and inversely proportional to the resistivity of the material. Rearranging this, we could have an equivalent definition of the resistivity is equal to the ratio of the electric field per current density. So if we interpret this, what this means is for us to maintain a particular current density, if we have a large resistivity, we're going to need a large electric field to overcome it to maintain a particular current density. Whereas if we have a small resistivity, then we don't need quite as large an electric field to maintain that given current density. Now, the units for resistivity is the ohm meter. Ohms, remember, is written as the Greek capital letter omega, meter. And this is the same thing as 1 voltmeter per amp. In thinking of resistivity, remember that random thermal motion increases with increasing temperature. Empirically, a larger potential difference must be applied to overcome the larger random thermal motion of the charge carriers. And this implies a temperature dependence for resistance. So we can say then, for conductors, resistivity depends on the temperature. Over a limited temperature range, the resistivity of most conductors may be approximated linearly. And that resistivity is equal to the resistivity at some reference temperature. That reference temperature is usually taken to be 20 degrees, times the quantity of 1 plus the temperature coefficient of resistivity, which we will call alpha. That temperature coefficient of resistivity is a property of the material. And that coefficient multiplied by the temperature at which we find our resistor minus our reference temperature, again typically taken to be 20 degrees, gives us our temperature dependence for resistivity for conductors. And again, rho naught alpha, our temperature coefficient of resistivity, and T naught all correspond to some reference temperature. If you change your reference temperature, then you will have a different value of rho naught and a different value of alpha, the temperature coefficient of resistivity. But typically, this is just taken to be 20 degrees Celsius.